So I can start where I left. So I will define, I will start by the definition of what soft matter is. By the way, is my voice enough? That should I shout more? Or do I...
It's already good here, I think.
Okay. And then I will try to give a brief explanation and some definition of molecular dynamics method, because we will today talk about, and in the hands-on session do some practice about the DPD, which is a coarse-grained simulation method. But you can refer as some CGMD, like coarse-grained MD, because it has some technical similarities with molecular dynamics. So I will try to be starting from a wider perspective and then try to go narrow. And then the part one would be, in general, what is coarse-grained and what coarse-grained simulations are, like the general concepts. And then in the part two, I will start to talk about what DPD is, some definition and background of DPD, definition and some technical details. I hope I don't bother you with too much equations, but it's always good to learn what is inside. And then I will try to give some examples from literature and also from our work. Actually, mainly from our work and partially from literature. So I will try to also advertise what we are doing so far, what I did previously, and what we have been doing in Track University. And I will just briefly explain what are the hands-on sessions that we have had. Actually, you probably saw in the EuroCC webpage what kind of cases, hands-on practice cases would be there, but I will try to give slightly more detail and what kind of properties we will try to study in the hands-on session. So I will start with soft matter. Actually, there was one person that already told about that family. So you were working on soft matter, so you were probably quite familiar. Actually, actually that was a question. So when I was doing my PhD, I had an office mate, and then he was also doing some electron microscopy, but he was doing on the technical side. So he was writing codes to analyze the electron microscopy data. And then one of the questions of the committee asked, what is soft matter? How do you characterize it? So many people are working with soft matter. Maybe most of you know what is soft matter, and you know the scientific definition of that. But at least I will start. I wanted to start. Maybe it would be good for the bachelor students. So these type of questions you might encounter in your master's exam, PhD exams, or whatever you do in the future. So how do we define soft matter? So we can simply define, or can we define as a material that can be formed? So some vague definitions that might continue, such that things that do not hurt your hand when you hit them, that might be the non-scientific definition of a soft matter. For example, is water and cornstarch mixture is by definition soft matter or not? Maybe I can ask you. Yeah, water and cornstarch mixture, for example.
Water could be a soft.
No, mixture.
Yeah, mixture.
Because you know that is a non-Newtonian fluid, so when you exert. So that is a different perspective. So it depends on what kind of forces you apply in order to be classified if it's a soft matter. So is it fluid or solid? So soft matter is actually, you can come up with many definitions, but as I already told you, you have to, or at least in my perspective, I want to try to explain things a little bit more physics-based explanation. So the definition that you might encounter in the physics lecture, in physics books, that this soft matter is type of materials that are easily deformed by thermal fluctuations and external forces. So what differentiates soft matter from the rest of the materials is the extent of the deformation that is a result of the thermal fluctuations. So that is a huge driving force to deform the material, at least this type of particle material. And by an external force, you apply some sort of an external force that can be mechanical force, can be other type of forces, which I will explain in the later slides. So you end up with a property of the material, which is elasticity and tension, and you have a different distribution of potential energy and kinetic energy in the system. So a couple of examples to the soft matter, which is actually might be quite interesting for the industrial community, such that hair gels, mayonnaise, shaving cream, colloidal crystals, polymer solutions, blends. So that these are the type of mixtures that are both interesting for the scientific community and also for the industrial people, because you end up with a customer and with an end product that's quite relevant to the customers. So these are mainly what's going on, at least in the soft matter community, which a lot of people are working in the collates. Today we will try to also briefly show some hands-on practice in the hands-on practice session, some formation of we cannot call it collate, but at least some micellization with the DPD simulations. So, to continue with soft matter, is it similar to ordinary solids and liquids? So, the main idea of trying to imagine how soft matter is actually when you go down. So I will also come to this later. But since you are seeing these nanoscopic building blocks, so soft matter is actually, you can ask this question if it is similar to ordinary solids or liquids. So that's one of the fundamental questions that you need to answer or in order to try to understand soft matter. No. So here, I mean, the definition of soft matter is that the individual molecules seem random and disordered like a liquid, but if you zoom in, you end up with a more ordered structure. So the intrinsic properties or the material properties of the soft matter are covered by, you can, for the macroscopic scale, you can try to think that these materials are more like amorphous or randomly distributed, but if you go down, if you narrow your line scale, if you zoom in, then you end up with more ordered structures, which actually are formed based on self-assembly procedures. So these building blocks might be spherical micelles, cylindrical micelles, lamellar phase. Then you increase the concentration, you end up with first spherical, cylindrical micelles and lamellar phase, and then when you still try to increase the concentration of, for example, a block copolymer in a solvent, then you end up with the reverse micelle, and you can also observe some bicontinuous structures, such as, for example, in metal organic framework, you see these replicable molecular subunits, and you also end up with a vesicle type of structures, which might refer, if it is lipid-based, we call it liposomes. If it is polymer-based, you can call it polymersomes, etc., etc. So that's quite different structure in comparison to spherical micelle. I will also try to show you some DPD results of ours on how we obtained vesicle type of systems. But we will try to do in the hands-on session the formation of self-assembly process of spherical micelles. As I already mentioned, soft matter is the structure and the properties is governed by the thermal vibration. So that means that we have a large response function. So a small change can dramatically change the properties of the system, and the external actually stimuli can be temperature, light, magnetic or electrical field. So you can refer to the self-assembly process by initially starting from amorphous structure, and then this amorphous structure or random distribution is ending up with a more ordered structure based on the thermodynamic properties to try to stabilize by means of the energetic properties of the system. So if you can also think that you have an amorphous structure, and below glass transition temperature you have more crystalline, you have a material that is more acting like crystalline, and if you go really down, you end up with a really crystalline structure, and if you increase the temperature, you have the melt. So for those of you that already doesn't know what glass transition temperature is, actually I wanted to put this brief information, because especially in the polymer type soft matter systems, you have a glass transition temperature that marks the temperature at which an amorphous polymer changes from rigid to solid, which is less freedom for the molecular subunits to fluctuate. Let's put it in that way, from rigid to solid to a more flexible rubber. So that's actually temperature is characterizing how the segmental motion of the polymeric material is. Here, what you see is actually that is experimentally and also in the computation-wise how you define a glass transition temperature. For example, you can this one. I mean, I didn't put a specific label to the vertical axis because that might be. I mean, in this case, that might be when you increase the temperature, a property that is decreasing. For example, when you increase the temperature, what you have the enlarged volume for most of the systems, and if you increase the volume, then you end up with decreased density. So what you have is a transition zone around glass transition temperature, and you can try to identify the glass transition temperature by different methods, but what it is slightly corresponding to somewhere in the middle. So you can try to both experiment to do this by TGA or whatever experimental method, and also you can try to mimic the same experiment with the computer simulation. So far, is it how is it going? Yeah.
Those sandals sign for what? TC. What kind of temperature? Like
that is. What do you mean? Like a normal temperature, like Kelvin?
what are the difference between the three of them? The first one is the normal.
Yeah, okay. Now you are asking what they stand for.
Yeah.
So this is melting, crystallization, and glass transition temperature.
The second one, what is it?
The crystallization temperature. So that is different what glass transition already mentioned, because you have limited mobility for the glass transition temperature, but the crystallization temperature is a temperature that which system switches to a full crystalline state.
And the last one for?
This one. This is glass transition temperature, so this is how we try to estimate. So this, I mean, I wanted to particularly put this slide in order to show you that soft material is a material that is already changing properties with respect to external stimuli. So that's why I wanted to show you in one of the slides, in this one, how temperature affects properties of soft materials in general. I mean, in this case, it's more like for polymer systems or all polymeric systems, but you can see this in different material types as well. So let's come to the length scales, because I already showed you in this slide. So when you zoom in, when you go down, you really end up in ordered structure, and these ordered structure are somewhat building blocks for the macroscopic structure. That is also the intrinsic properties embedded in this ordered structure, such that you have alternative or different material properties at the macro scale. So the soft matter, if you want to study soft matter, then you really need to go down. But if you go down really low, you also might lose some of the structural properties, such that I don't want to show this slide again, but in the spherical micelles. So that is a length scale that is associated with the soft matter, if you really would like to understand the soft matter. So that is actually falling in between atomistic and microscopic scales. So somewhere in between, so in which side that is debatable. So you can try to build some study of approach in order to make yourself more associated with the, acquainted with the atomistic side, or slightly close to microscopic side. But in general, the soft matter is, the length scale that are associated with the properties and dynamics of soft matter are called as mesoscopic length scales, which is, I will repeat again, which is in between atomistic and microscopic scale. So mesoscopic, you will also, you might read and hear about this mesoscopic scale. Meso is actually the Greek word which means in between. So that's why I already told you on which side you are more close, so to the atomistic side or to the microscopic side. In our case, what I do, we are trying to approach the problem mesoscopically by keeping ourselves slightly closer to the atomistic side, because we want to study the formation of these building blocks. That's why DPD, the distributed particle dynamics, or the other coarse-grained simulation methods are often referred as mesoscopic simulation methods. But mesoscopic is, as I already told you, debatable. For example, if you go to a mechanical engineering department and talk to a guy that is already the particles that are actually interacting, so the dust in the air, that's a quite interesting problem. So later, Albert Einstein and the Polish physicist Marian Smoluchowski, I'm always having trouble to pronounce, Smoluchowski, explained the Brownian motion by a statistical-based, mechanics-based explanation of the movement of pollen by the force exerted from individual water molecules. So that is there, which you already try to explain macroscopic things, the things that you can see with your eye, by the things that is already governed by at the atomistic or mesoscopic lens. Okay, so I can close the parenthesis now for the Brownian motion case, but as I already mentioned, for the soft matter, and in order to understand what's there, you need to really know what's going on the molecular scale. So Pierre de Gennes, this is probably all of you know, already gave a definition of soft matter in his famous Nobel Lecture Prize speech. That he also referred, or he already mentioned that the soft matter are referred as by some people, complex matter or complex fluids. So that might be scary. Some people are referring as still soft matter, but by definition, complex matter or complex fluids are in the same line with the soft matter case. And these materials, I want to emphasize again, that are forming based on the molecular building blocks, and then you end up with the materials that have some special intrinsic specific properties. So in this lecture he actually showed this cartoon, which is actually showing that the various animals attempting to follow a scaling law. So what is important to understand the scaling law, I'm not going to go deep in the scaling law, but at least we started by referring to building blocks, and this in the cartoon he emphasized that the various animals attempting to follow the scaling law, such that you have building blocks for a more complicated, for a more complex structure. Actually, you can see this also in Picasso in the famous drawing of the bull, such that he ended up with a really naive and cartoon representation of a really complicated drawing of a bull. So there's one more. So there was a TV series, Lost. How many? Maybe I can ask how many of you already watched Lost, because I will end up in very few. Because I saw 1, 2, 3, 4, 5. Okay, maybe 10% of the audience. Okay, maybe 15%. So there was a bald guy, and his name was John Locke, but he's not the same John Locke. That guy was also slightly philosophical on the philosophical side. But the philosopher John Locke already gave an explanation to a complexity. So that's a long sentence, but I will bother you by reading this long sentence. So according to John Locke, the famous philosopher, the complex idea of a substance is a collection of simple ideas that is believed capable of existing independently. Observing experiments that several features recur together frequently, we suppose that there must be some common subject that has all of them. So that is, I got from a different web page, but that is in one of the original books of John Locke. So he already dragged our attention to the level of complexity, and the complex ideas, in a more abstract way, are composed of some thoughts that are already building blocks. So that is quite similar to what we try to do in material science or chemistry, physics, or in mechanical engineering. So if you're really dealing with soft matter. That is also, maybe you already heard, I didn't put in this slide, but you have this Occam's razor. So there is a complicated situation going on, and usually they say the simplest explanation is valid, or you can also transform that thought to the simplest intrinsic behavior. The complex behavior might be governed by a simple fundamental property, which is already somewhere in the bottom for the soft matter case. Okay. How's it going so far? Okay, so now we can try to switch what kind of soft matter, at least I'm interested, or maybe some of you are interested as well. I know it's time. Okay. The soft matter is actually that we are interested in is, you can see in the slide, so we are, so this is not, of course, the huge, the wide range of materials that you are associated with if you are really dealing with soft matter, but building blocks such as cellulose and surfactants, you were working with surfactants, and surfactants that are forming some microscale ordered micelles, or for example polymerization and polymers or oligomers that are already in the range of widely studied soft matter case. If you really would like to if you are really interested in biological materials, then DNA, for example, or RNA, or so this was the structure that I did in my graduation project. That's why I made it a thought, okay, I should put it here. Is a voltage-gated potassium channel that is already giving some thermal fluctuations and fluctuations that is associated with the interactions in between. So that is already can be classified as soft matter and the building block. So what you can see in all of these structures is that you have the building blocks, and then you end up Voltron. Probably you're. How many of you don't know Voltron? Okay, very good. Because some of them I'm. Okay, I will also put another parenthesis maybe to distribute the attention a little bit. I'm also teaching heat and mass transfer in the university to our third-year students. And in one of the main topics is the diffusion model. So you talk about the flux. When I always start to talk about flux, I'm always asking how many of you watched Back to the Future. And believe me, just from a class of 70 students, just 1 or 2 students raising hands, they don't know. And then I'm just there, I cannot start the topic because I will start to talk about flux, but then I cannot associate with the concept. So that is. That might be sometimes a little bit dismotivating. Okay, so these are the materials that are already there for the microbiological side, and so this slide is more like summarizing what I already told you. That we have the soft matter, which is typically composed of nanomeso building blocks that are easily deformable when exposed to weak external fields, like flow fields, like microfluidics, mechanical forces, electrical magnetic fields, thermal agitation, and the examples, in addition to what I already showed you, is paint, blood, milk, spreads, and ice cream. Especially these are particularly important in the industrial area, for the industry guys, and often formed as a result of self-assembly methods. And what we need to establish, or in order to try in the soft matter field, is the fact that, I mean, we are motivated to study soft matter because if you really would like to understand what's going on, a quantitative description of this heterogeneous hierarchical non-equilibrium soft material is necessary. So, that might be in living systems or in synthetic side. So you really need to quantify things, and here I can switch to. A couple of slides. At least you can try to use molecular simulations in order to quantify the structure or the properties at the really mesoscopic or atomistic scale, which is quite relevant for the soft matter side. Okay, so yeah, this is just from a paper because that gives a nice overview of what kind of self-assembly process, because I already talked about self-assembly, so you can already start to think about what kind of kinetics that are associated with self-assembly. So this is actually showing some brief information. That's a quite nice paper actually. That's quite new, but that gives a nice overview of what kind of kinetics that are associated with the self-assembly process. So you have different relaxation times. You have fast relaxation times in microseconds and slow relaxation time in seconds. And that's, this equation already gives you the properties that are composed of the slow relaxation and the fast relaxation. And then, for example, you might end up with the random, starting from an initial random structure, a structure that is already aggregated, which we'll also see in the afternoon hands-on session, from how the random distribution of particles will end up with a more ordered distribution of particles. And if you end up with such properties, you can try to estimate what kind of relaxation processes are incorporated in this micellization or aggregation process. Micellization and aggregation are different, so I don't want to use them as synonyms to each other because they are different physical processes. So I can actually skip this slide quite fast because I wanted to show you, just to show you what kind of, if you are really studying college, maybe I thought if there's someone that is working in college, then that might be a nice literature to have a look at, because then in college also the kinetics, the kinetic properties, or the kinetics actually, are governed by the formation of self-assembly structures. So initially you have a different distribution, and then you start to see a slow diffusion process that is ending up with the ultimate colloid structure. But all in all, molecular level information is actually necessary. I hope I've already convinced you to how important molecular level information in order for you to understand what's going on in the soft matter field. And in order to rationalize the experimental design, nowadays actually still molecular simulations can be viewed as some, in some actually fields, not in all fields, but in some fields still like toy models, but actually believe me, they are, if you're really careful, these are not toy models. So there's a famous...
sorry for interruption, but is it possible to simulate also work with the DPD for the surface modification of nanoparticles?
Yeah, I will show you some examples. Oh. In principle you can, but you have to be careful. So, actually yesterday there is one famous book that is being taught if you are really taking molecular simulation classes, which is from Ferenc Smith and Dan Frankel, Understanding Molecular Simulation. So yesterday, Dan Frankel received a prize, Lawrence Prize, so they call it as the sub-Nobel Prize, or the Dutch version of the Nobel Prize. And one of the other famous professors in one of the slides, they show, I only believe, so this professor was experimentalist, I only believe simulations if it is performed by Dan Frankel. So it is not the case. Of course, you have to be careful in try to at least try to interpret the data that you obtain, and in order to validate your simulation parameters. So you have to be careful. Okay, so we've already talked about mesoscopic and atomistic scale. So that means we are actually in a length scale and time scale plot. We are somewhere here. So you can try to employ some atomistic simulations in order to see what's going on at the nanoscale. And if you slightly go up, you can try to see what's going on at the mesoscopic scale by coarse-grained simulations. And often DPD, so Brownian dynamics, Boltzmann simulations are in the class of mesoscopic simulation. Now, this is an old plot, but nowadays they have other coarse-grained simulations like Martini or other MD-type coarse-grained molecular simulation methods. But actually, personally, I'm not interested here or there. But if you really try to go beyond what's going on at the mesoscopic scale to the macroscopic scale, like the formation of really the materials, etc., You can employ finite element or computational fluid dynamics, or if you really understand what kind of reactions are there for particular type of systems, then you need to go to subatomic level, to the electronic structure property estimation approaches. Okay, so the introduction for the soft method part is over. Now we can go to the molecular dynamics. Briefly, what's happening in the molecular dynamics, what does it refer to? Maybe most of you already know what molecular dynamics is, but I thought maybe some of the people that are already far from the field, so I just wanted to give some brief information on MD. So molecular dynamics is actually, so what you solve is the classical equation of motion, which is Newton's equations, for a set of molecules. So that is what you do. So that's quite, I mean, the physics behind is not quantum level physics. So what you have the potential, you can estimate the forces, and from the forces you estimate the acceleration. So I will show you how you integrate the position of the particles in time, but mainly these equations are there, and you solve these for a set of particles. So initially, the first example of MD is actually the hard sphere systems. You have a discontinuous potential and smaller than this potential. So you have a hard sphere system basically. So when the particles come to a specific distance, the interaction energy is finite or infinite, or for the rest is zero. So the initial examples for this hard sphere system is Bernie Alder and Thomas Wainwright, and they performed with IBM 704 at University of California, a radiation lab at Livermore, with this machine, solving specific set of particles and how their time evolution is covered. Actually, yesterday I found this picture from a different, I don't know, it was quite relevant. I was just looking at the Twitter, and then I saw one of the professors that are doing molecular simulations already attended the SEICAM meeting in Lausanne, and then they were actually giving all their prizes. So they have SEICAM, maybe you heard about this organization, or if you're doing simulations, you can try to follow their workshops. They are quite famous, so I can just write here. This is an organization in French. It's a European Molecular Modeling Organization. So they do different workshops for different level of simulations. So for your thesis, for your work, you can try. If you haven't heard about it, that's a quite nice organization to follow the lectures of very famous people. So yesterday, actually, they were giving the prize of Bernie Alder to Kurt Kramer. Maybe you heard about him because he's a very famous molecular modeling guy in Max Planck Institute. So this year he received the prize, and then in one of the in his lecture or in another lecture, they put this picture, which Bernie Alder is the standing guy with Mary Ann Mansai. She was the coder, by the way, and Thomas A. Wainwright, the physicist, is actually working on how the coexistence of crystallites and melt for two-dimensional system of elastic disks as predicted by initial molecular dynamics are there. So maybe you can try to understand the order of the elastic disks and in two dimensions how they generated the particle distribution. So these are the initial examples. So that's quite important and quite for me. I mean, for me at least, it's quite important to see the early examples of molecular dynamics. Actually, I haven't seen this photo before, so for me, I was quite happy to see this. And later, the methods of the discontinuous potential is switched with the continuous potential by Anisur Rahman. They actually have a song written for him. I don't remember, I don't recall the song. If I find, I will try to share it with you. And then he started to work on the particles characterized by the continuous potentials, and that leads up to the simulations of realistic atomistic models. And Frank Stillinger still luckily still alive, and performed the first MD simulation of liquid water. So if you're really working with liquid water, if you're trying to simulate, you will end up with a huge pile of papers that you need to cite. If you write something about the simulation of water, Stillinger's papers are there for you. So this is a new paper. So if you are really interested on the background of statistical mechanics-based molecular, the statistical mechanics and the molecular dynamics, and how it's applied to the protein dynamics, so that is a recent paper by Machulia, Rowe, and Cicciotti. It's actually published in August 2022. So that's a quite nice paper giving the history of what is there for the molecular simulation side. Okay, so for the MD, so that was more or less the introduction. So how do we carry on the simulation? So we need, as I already told you, to solve equations for a set of particles. So that means you need to define your system based on the set of particles. So how you define your system? Probably most of you already know, but with the Cartesian coordinates, so you have a molecule, and then you have the coordinates associated with the position of the atoms in the three-dimensional space. So in atomistic simulations, you have this fundamental approximation such that, or underlying assumption, you have the Born-Oppenheimer approximation such that the wave functions of atomic nuclei and electrons in a molecule can be separated because the nuclei are much heavier than the electrons, and the coordinates of the nuclei in a system are somewhat fixed, while the coordinates of the electrons are dynamic. So that means if you carry the nuclei from point A to point B, then the electrons are also going with them. So you really need to assume that you don't have an explicit definition of the electrons, because otherwise you will end up with a huge pile of other type of equations you need to solve. So that is the most step that you switch from quantum level approach to a classical mechanics-based approach. So the main message for this slide is you define your system by the three-dimensional Cartesian coordinates. So what you do, as I already showed you, then you need to compute the forces associated for this set of particles. So that you have a collection of set of particles, and if this is a soft matter system, that might be starting from a random distribution of particles, or you might really start from an ordered structure, because now you have tools which we didn't have in the past, that you can directly start from a self-assembled structure. So you can build your system initially by, if you know what type of end structure the system has. For example, if you are really working on liposomes, you can start with the formed liposome. So that's also a nice thing to do. But at least you need a set of particles, the collection of particles in your system, and you need to compute potential energy and switch to the forces based on the position of this set of particles plus the velocities. And you solve the equation of motion, which I will come briefly in one or two slides later, and sample your data after some time steps. So time step concept is important in molecular dynamics simulations, because you need to understand or see where the collisions are happening, because then you need to estimate where these particles are going. So that you need to observe the proper collisions in your system. So if you can discretize your whole simulation time to smaller time steps, and if you take it too small, then you would end up really in a low level of integrating time steps. If you make it too big, then you have unrealistic collisions, which you might end up, you will for sure end up with unbalanced energy in your system, uncontrolled energy. So you need to take a proper time steps in order to model these collisions. So this time step concept is, we'll come to this one later. So here in this slide you see a simple molecular dynamics program. Actually I told you about the book, so I took this slide from the book. So that's in a very simplistic way. So what you do in a simple MD program, you initialize your system, like meaning you have an initial set of particles which has on average, the system has an average kinetic energy such that you try to target a specific temperature, and you start, as I already told you, if you really know what your system would look like, you can build your system based on that morphology or based on that structure, or you can start from a random structure and try to end up with the targeted three-dimensional structure. And the MD loop starts actually by computing the forces, integrating the equation of motion. I will come this one in the next slide. And you, at some intervals, at some time steps, you actually compute the averages. So that's what's more or less going on in a simple molecular dynamics data. So I already told you about the integrations of motion. So how do you actually integrate? Because if you solve the F is equal to ma, you end up with the acceleration. So you need to actually use this acceleration and velocity and the positions of the current particles to estimate the particles that are actually at the next iteration. So that is called as Verlet or velocity Verlet algorithms. So you actually have a Taylor series expansion around the F is equal to ma or around the force, such that you have the positions of the particles at some time step later, and the current position of the particles, you have the current velocity and the time step, and then you have the F equal to ma, the m's are cancelled, you have the acceleration, and the rest of the ordered terms, which actually usually are ignored. So you have, you can make it one step further, one step back, and if you add these two terms together, you end up with this equation that is called the Verlet algorithm. So you don't incorporate velocity in the system. So you can modify the Verlet algorithm by incorporating the velocities, velocities are important in order to control the temperature. So you need to estimate the kinetic energy in order to compute the proper level of total energy plus the temperature. And that means you need to, that is much better if you incorporate the velocities in your equations of motion. So the equations of motion are usually often in molecular dynamics data are used based on this, but they have different versions of the Verlet. I'm not going to go really in deep, but if you really are interested, I can give you some later after the lecture, after today. You can just, I didn't put my email, but if you just Google my name, you will end up my webpage. So you can just send me emails whenever you want about the topics here, so you can just exchange information with them. Okay, so the equations of motion are governed by mainly velocity Verlet and Verlet algorithms, and then I already told you about how the potential energy of the system are characterized. So this is actually a physical chemistry class, so that is already associated with how you compute the potential energy of a molecular system. So you have what you might have in your system is the intramolecular interactions and intermolecular interactions, so which is already in between the same molecule or in between different molecules. So we have in between, in a single particular molecule, we have the bonded potential and the angle potential for the bond vibrations and angle vibrations, and we have also the torsion potential, which is already associated. I will show you in the next slide a more clear demonstration of what is there with the torsion that is associated with the atoms on the same chain that are separated by two atoms. So you have these intramolecular interactions, and you have also intermolecular interactions that are referred also as the non-bonded potential, and you know the van der Waals potential. And the most common procedure to model the van der Waals potential is the Lennard-Jones potential. Here you see one of the typical examples of Lennard-Jones, equation. But you can see another. I will also show you later that these prefactors and the powers might change, because that is also associated with how you fit your available data to parameterize your force field. I will later come back to the force field concept. So this is mainly what you need to define in your system. if you really would like to perform molecular dynamics or coarse-grained molecular dynamics, or DPD. That is quite similar in concept. So in molecular dynamics, actually what you really would like to see is the sampling of the structure that are associated with different local energy minimums. So that means that is actually what separates molecular dynamics sample the most number of possible conformations in your system. But now with the availability of computer power, you need to also pay attention to the simulation time. So that's also quite important. So what molecular simulation people do, they actually sample. So that is mainly statistical mechanics based approach. So I'm not going to go deep on that side. But I just want to say here that your system, your molecular dynamic system, is a collection of particles that are statistically representing your system of target, system of interest. And what you do, you may as well compute all the possible interactions for the bonded, for the angular potential, for the non-bonded interactions, for the hydrogen bonds, for the electrostatics, etc., etc. But you don't do that for the sake of computational time. What you do instead, you take a cutoff and you identify a particle when you're solving the potential around acting or the forces that are exerted on that particle from the rest of the particles. Then you select this cutoff and then you try to compute the interactions of this specific particle with the rest of the particles that are within this zone that is characterized by this cutoff values. So that is actually showing that one. Plus, I already told you that you already have a system of a replica system of interest, such that you have statistically your system represents what you would like to achieve, and then you actually employ most of the time periodic boundary conditions, which means that your system is replicated at all dimensions. You have the replica of your system. So that is a nice, really nice, very yet simple thought, such that you also at the same time conserve the number of particles in your system, because number of particles in your system are especially important if you really would like to consider a statistical based canonical and microcanonical ensembles. So, for example, the particles are fixed. That means the number of particles are fixed, such that the periodic boundary conditions imply that if your particle is here and then if it is switched to this zone, that means that the same particle is entering the same box from the other side. So that is periodic boundary condition, and that's how the periodic boundary conditions are like this. Okay, so this is might be slightly more technical, but I just wanted to tell you about what kind of boundaries we are talking about, because in molecular dynamics you really need to think about the boundaries, because the particles are moving. So what happens if they are hitting a wall? That's a completely different system, so you need to consider that as well. So I already talked about the computational efficiency, and I already talked about the cutoff force. So how you implement this cutoff to your system? By actually shifting and truncating the Lennard-Jones potential. So this is one formula of Lennard-Jones type of equation, and you truncate. That means if you have a cutoff, you cut it. So this is a typical Lennard-Jones potential. I would like to call not Lennard-Jones potential, but Lennard-Jones equation, because that's more associated to Van der Waals potential. So you cut the system, but then you end up with a zone that is already negative energy on this side. But if you go slightly above, you have zero interaction. So that is associated. I mean, that leads up to numerical errors. So what you do, you cut your system and you shift your Lennard-Jones potential, such that you end up with this type of treatment of the potential energy. That means you remove the discontinuity at the around the cutoff. So that's quite important. So for example, I'm also teaching molecular modeling. So I'm always talking about if that means like hitting the wall and you're going 100 km/h. So that is, if you really would like to model the collisions, then you don't need to cut the force that is exerted on particle or the interaction between particles instantaneously or right away. So you need to treat also a smooth. I mean, you can make a smoothing potential, but what is mostly employed is that the truncated and shifted length potential. Okay, so this is the main portion that the conservative force, which I will also talk about in molecular dynamics, are leading to the end structure, and the conservative force are associated with the forces that I already told you, the Lagrangians and the intramolecular bonded and angle potentials. Okay, so in this slide, you remember I already told you about the initialization of the system. That means I told you that you can either start with a random structure or you can start with an order structure that is interest for you. So if you are really starting with a random structure, so you can imagine that on this potential energy surface, you cannot imagine how far you are from your target of from your target. I mean, from your target potential energy. So that is quite an important challenge, because you need to first, at 0 Kelvin, without any incorporation of the kinetic energy, you need to decrease your system's potential energy to a really feasible level, because you are starting from a random initial distribution that is quite unrealistic and unnatural. So there are algorithms for, which we call it energy minimizations. They are actually optimization algorithms, so you can use these algorithms for solving some other industrial engineering problems, etc. So briefly, they are what are mostly used: steepest descent, conjugate gradients, and Newton-Raphson. But as I already mentioned, I mean that like such as Monte Carlo, you end up in the local minima that are actually dictated by the gradient of the energy or the gradient that are. I mean, it depends on where you are in the potential energy surface. So that means if you are at point B, by employing these algorithms, you end up here. If you are in point A, you end up here. So, but if you really would like to go to here, you cannot use energy minimization. So that is there. So you have actually first order. I mean, you take the first derivatives for these ones, and you take the second derivatives for the Newton-Raphson method. So Newton-Raphson method is more complicated, so you don't really employ. You don't want to employ because building the Hessian matrix is really time-consuming. So you start with the really first order energy minimization, and then go to second order approaches. So to compare, yeah, this is just to give you some idea. The performance of these two methods are different from each other. So, for example, if your gradient is high, I mean that means you are closer to what your initial structure dictates. For example, in this, the numbers indicate that the steepest descent algorithm performs much better than CG. But if you really go to the shallow zones in your potential energy surface, that means you need to switch to CG conjugate gradients, because the steepest descent are performing much slower. So that might give you some idea that for the difference. I mean, the mathematics are different in between two different methods. Conjugate gradients has a particular set of equations that you need to solve, but the steepest descent you decide your step sizes based on the gradient, actually, where the minimum, the maximum gradient is. Okay, so we already told you about the F is equal to ma, and that means we can start now talking about the force field approaches. So what force field is, and how do we compute the force field parameters, and I will also try to give you some force field, most common force fields that are associated with the synthetic polymers. So I'm not going to talk about really biological protein simulations, because I'm not really an expert on protein modeling. But for the synthetic side, I will try to give you some brief examples. So I already showed you the bond stretching and angle bending. But we also talked about the bond rotation. Actually, the people refer as a bond rotation or the torsion, but at six, it is actually an interaction. I mean, if you really look at the physical chemistry side, that is the interaction in between this 1, 2 and 3, 4 bonds. So these bonds, I mean, the repulsion in between are actually dictating the torsion. So you can also consider it as a non-bonded interaction, but people always refer it as the bonded interaction. So that's okay. We will also keep it that notation. I already showed you the physical domain, Newton's equation of motion. You have potential. You take the first derivative, you end up with the force, and then you have the velocity and the positions and their differentiation, and you to get the A. You also have non-bonded interactions like electrostatics and van der Waals. So I can also, yeah.
Can we say that we actually neglect all these forces when we use DPD because it is more or less related to mesostatic?
You cannot say that. Yeah, you cannot say that because the DPD now is going really on the side that is quite similar to this one. But the original DPD do not consider this type of interaction. But this one, yes. So this one recently, yes, but previously no. But these ones, yes. So DPD, as I told you, that is also practically it's not 100% physics-based molecular dynamics approach, but you need to solve equations of motion and you need to compute the potential energy. So in that respect, you need to solve these ones. But recently, DPD already incorporates some electrostatics, so that is a nice approach. So DPD is becoming more and more developed, so that is also nice to see. So the mathematical equations for the bonded forces, you have the harmonic potential. For the angles, the harmonic the same, and for the torsions, you have the cosine term because you have the rotation. I already showed you the Lennard-Jones and the Coulomb interactions for the electrostatics. And for the force field examples, I already told you that we have the OPLS with the. So these are also OPLS is also used for synthetic systems, so that's why I put you and I put it here. So that is actually, I think, what was it? Optimized potential for liquid solutions or something. Yeah, I think it was something like that. So there was also another. So that's why I put you for, because I told you that Lennard-Jones might differ based on how you optimize your parameters based on a specific equation. That's why I don't want to call it Lennard-Jones potential. So that is actually an equation. So the factors here and the powers might change. So for example, OPLS uses a 12.6 potential. So these are 12.6, so the powers. But if you go to compass, you have the 9.6 potential. So compass is also very developed potential for the synthetic systems. Unfortunately, this one is not available. I mean, in lamps that is available, but previously it was not. And you need to buy this. I don't want to give. Okay, now they are recording. I don't want to give the name of the software, but you need to pay a lot of money to purchase the software in order to reach to that particular force field. So, but now recently they also incorporated in labs. So, I'm not sure how they did it. I don't want to know, but probably it's legal. So we have also an old one because that's the 90s from William Goddard. I always like this guy's name because you see that is like remembering the kings to me, William Goddard III. And then the old force field, but that is actually really performing really nice in also for the biological systems, because you also have a specific explicit treatment of hydrogen bonds in Dryden force field. So that is also nice. And you have also previous version of the 9.6, the compass with CFF. We also have PCFF, etc., etc. Okay, now I can start with the course grain. Maybe we can give a break. I don't know how long the break?
15 minutes.
15 minutes. So later after the break, we can continue with the course grain. already about the force field, about the DPD, so you probably you know how to reach me, because just type my name in Google and then you can see my information there. Okay, let's start with the coarse graining and coarse grain simulations. So far I already told you about the atomistic representation of data, and I even showed you one typical example of what kind of representation of a 3D coordinate file can be. So coarse graining is actually what I mean, we can start with what is the coarse graining. Is actually we are smoothing out of the atomistic detail. So you have an atomistic representation which is based on modeling or representing atoms as point particles in space, in three-dimensional space. So in coarse grain representation, that is the same. I mean, this representation is valid as well, but instead of atoms, you try to build larger particles which are representing chemical functional groups. So that is one of the interesting definitions of coarse graining. The coarse graining is, as I said, that is smoothing out. I mean, that means smoothing out of the atomistic detail, and you actually lose the degree of freedom, because the less detail, less degree of freedom that is associated with your system. So you can make coarse graining in different ways. You can combine small atoms such as hydrogens with the heavy atoms, and you can make superatoms, or you can also call this case as united atom representation. For example, these protein modelers are using this one. For example, they want to combine hydrogens because you have so many hydrogens, and they are usually dictating, of course, the hydrogen bonding interactions and ultimately the end structure. But nevertheless, you really would like to decrease your computational time, and then you try to assign a larger particle, or you need to represent larger particles in your system in order to, as I say, for the sake of less complexity. So this is, by definition, a united atom representation. So you can combine, for example, 3 hydrogens with 1 of the C, and 2 hydrogens with 1 of the C, etc., etc., and you end up, for example, at a decreased degree of freedom in a significant portion. Alternatively, you can, as I already mentioned, combine whole functional chemical group into a single entity, and then you can refer to this one as a coarse grain B. So this is a schematic representation of what you might see. So you have a functional group here, another one. So you have, for example, 4 water molecules. So these 4 water molecules are combined to represent a particular bead. So as I already told you in the previous slide, that you lose the atomistic detail inside. So what you have initially, atomistically, 4 representation of 4 water molecules, and if you coarse grain these 4 water molecules, you have 1 particle position in space, and then this is actually representing your coarse grain bead. So that might sound a little bit unrealistic, but the physics associated with that are actually trying to compensate this loss of degree of freedom. So this for water, I mean, so you always in the coarse graining, that is a quite, if you are really using DPD, so if you are not using Martini type of coarse graining, and if you are really using, for example, DPD type of or of a coarse graining, or if you're really using a coarse grain method that you want to build by yourself, then you need to pay attention to the, so you need to have some chemistry knowledge in chemistry inside, because you cannot cut, for example, a benzene ring from half. I mean, you can do that, but then at the end, that might give you some other troubles if you're really computing the potential. Because in MD, I already told you about the concept for force field, and in MD, in classical atomistic simulations, you have molecular dynamics structures governed by a certain force fields which are available in the literature, on the programs, etc., etc. But in the coarse grain simulations, that is different than that. You don't really have a set of force field, especially for DPD. You need to compute by yourself. So you need to consider what kind of coarse graining you have, which coarse grain bead represents which molecule, etc., etc., and you compute the interactions in between these super atoms, or we call it beads, by yourself. So that is most tricky step of the coarse graining if you are doing DPD. There are other coarse grain methods like Martini, I will also show you later. That is involving some level of force field approach, because you have a Martini force field, but still there's a huge gap in the modeling of this of the variety of systems with the Martini, because the parameters are not there. So you need to pay attention to the validity when you are validating your system, if you are doing Martini type of system. So here, I mean, our beads are there, so we are representing chemically meaningful functional groups. So for example, here you see a lipid. I'm not sure if it's phospholipid or amylolipid, whatever. But you have the hydrophilic parts and you have the hydrophobic parts, so you can have a 3-bead representation. So that might sound far from realistic, but as I told you, you have advantages, but you also have disadvantages. So you can have different.
So from the chemistry point of view, can we say that we group two atoms with similar electronegativities?
Yeah, that is more. I mean, based on functional group. For example, if you are considering an epoxy, you don't really cut the reacting part into two. For example, you want, or if you are, for example, modeling a polyurethane, so you don't want to cut the cross-linking junctions into two. So you want to combine them together such that you have a proper modeling of the reactions. So that's why you need some sort of chemistry knowledge if you're really using DPD type of approach. Different levels of coarse graining is there. So this is from a famous paper, which is quite nice. So you can have a look at it. One of the early reviews of the coarse graining approaches. But you can see that they have consider different level of coarse graining for bisphenol A polycarbonate. So you can have, for example, if you have a repeating unit here, so you can have a 2-bead representation of a repeating unit. So that is, as I told you, different than what you saw in the previous slide. And or you can have a 4-to-1 scheme, which has 4 points per repeating unit. So you can either use geometrical center of geometry or center of mass, or you can also identify a point that is vaguely representing this coarse grain bead. So that is when you start the coarse grain, you, as I told you, you just lose whatever is inside. So here, that is, that leads us to the fact that we need to, as I already told you, we need to compute the interactions in between these coarse-grained entities, coarse-grained beads, which is quite different than what atomistic simulations dictates to us. I will come back to this later. So when you coarse-grain your system, when you represent your chemical groups as single entities that are, again, points in space, but you don't have any atomistic detail inside, so what you end up is actually a different level of potential energy surface. So here, for example, on the left, you see an Ollerton representation of a potential energy surface, and here you see a coarse grain, which is actually less rugged. You can see that all the local minima that is associated with the conformations of the Ollerton system are gone, because you actually remove all kinds of side groups, hydrogens, and combine heavy atoms together to represent them as a 1, 2, 3, 4, 5, 6 bead representation, considering all this complexity. You can see that all this complexity decreases to this one. So, but still, you see, that is a nice feature of coarse grain simulation. You can still see the depth of the, the locations of the minima is still there. So even if it is less rugged, that depends on what you are, of course, interested in. That is, what level of complexity are you interested in? If you are really want to model this structure, you can start to employ. But if you are really going to the, that is also important. They call it NE, like non-equilibrium ME type of systems. Then coarse grain simulation might be a little bit less attractive to you. the advantages of coarse grain simulations, they have, as I already told you, less rugged potential energy surface. So that means you can overcome these barriers quite fast, and then you end up with simulating longer time and length scales. So why you are simulating longer length scales? Because you don't need to really go all kind of local energy minima, but instead you have a less number of energy minima. So that means you can run longer simulations. You can go higher length scales. Why? Because you are representing, for example, 4 atoms as a single bead. So that means you enlarge your system, and you have the dynamics associated with the larger system. I will also come to this one later, because coarse grain potential might be also different than a typical Leonard-Jones equation. Sorry, I forgot to say the rest of the advantages. So the other advantage is the faster equilibration of polymeric or complex soft matter systems. However, there are also disadvantages like poor performance in sampling local minima. As I already told you, that might be important for an EMD type of systems, and less ability to compute the energetic properties, because you don't have a proper definition of, although you have the chemical representation and effective potential, but still losing the atomistic detail might lead to some less energetic incorrect energetic properties. Because here also you can see that the narrow potential energy surface is also widened, so that's also another issue. Loss of ability to perform unequilibrium dynamics, so I already told you that, and that's also quite correct to say, fail to predict some, like mechanical properties. So you can also ask, why are you using this? I will come to this one later. That's also important. I mean, that has advantages, but also it has also disadvantages. So the atomistic detail, I mean, smoothing out, which means integrating out, or you can also call it losing the atomistic detail, leads to the effective pairwise interaction. So if you have a set force field for atomistic simulations, that means you need to have force field, and you don't have a force field, especially for DPD, but you can build your force field for yourself to define these effective interactions. Actually, what I just said is also changing now, because now also people are spending too much time in building force fields like DPD for systems like DPD method. For Martini, you have a force field, because for systems, for a range of biomolecular systems, you have. But for DPD, we were not able to have this type of potential, but now so many people are working in DPD, and they are paying a huge attention to this one, and then now we also start to see papers that is actually building generic force fields for DPD simulation. So in the future, in the near future, DPD will become much more versatile too. I mean, we are also, as group in Trakya, we are also one of the contributors. We are specifically, I will show you later, but for some liquid mixtures and their 3-dimensional properties, we are also invest so much effort to building a potential. I will show you some examples later. So, but I mean, by definition, you need an effective pairwise interaction, and the interaction parameters are not differentiated based on different systems. For allotum simulations, and the coarse grain model is different, as I already told you. For example, if you are considering the coarse grain model of polystyrene, that is different than polyisobutylate, because they have different level of coarse grain. So how does effective pair potential differ? So that is another concept. So that is the initial thought. I mean, that people are already aware of the changing of the effective potential in comparison to Leonard-Jones type of approach. But this paper is actually very nice. Time to time I reread this paper, which is really nice, which is from Forrest and Suter from ETH. So they actually compute or consider polymer mass, and they do actually time coarse graining. I mean, time coarse graining, you can also discuss that this time coarse graining might be associated with the ensemble averages because of the ergodicity. So you know about the ergodicity. So the hypothesis that the time average is equal to the ensemble average from statistical based mechanics. So if you are also, doing the time coarse graining, then you can also start to think about the coarse graining based on the length scale. So, in summary, these guys actually, even in their abstract, they start to talk about the rapid fluctuations and the integrating out of the rapid fluctuations, and in order to get the slowly moving mean conformation of the chain. So, what they ended up with, the interaction between the non-modeled pairs of atoms by this pre-averaging over these rapid fluctuations leads to a softer effective interaction. So that is the key point of coarse-grained simulation. So you have the Leonard-Jones type of potential, but then you can consider the integration out of the level, fluctuations at some time intervals, and then if you build another effective potential based on this mean fluctuation, a slower level of fluctuation, you have a different potential. So these guys schematically modeled in 2 dimensions as a polymer belt. They actually considered different levels of hydrocarbons. Not hydrocarbons, it's just carbons. Like C71, C40, different chain lengths, but it's just carbons. And then they actually consider the fluctuations of atom, and then there is also mean position, and then at different times we have a different mean position, which you can see here. But what is interesting for us and for you is that we have typical van der Waals type of potential, which is modeled by Leonard-Jones potential. So when you average at longer times, which is actually practically means that your level of coarse grain is increased, either time coarse graining or landscape coarse graining, your potential start to become much softer. So we have this van der Waals, you have this dotted line, and you have this much softer potential, which is having the larger level of coarse graining. So that is the key intrinsic and a nice feature of coarse grain simulations. You lose atomistic detail, but then you end up with a much simple, yet much versatile type of potential, which leads you much faster equilibration times. Because in polymeric systems, especially if you're considering polymer melts, like longer chains, you really would like to get rid of all kind of short range high repulsion, and at the long range, the long range is okay, it's going to 0, but at least for the short range you have a high degree of repulsion, which is actually preventing you to reach to the ultimate global minimum. So in the coarse grain, in the much softer potential, that means if you have a energy level, if your system is belonging to an energy level, that means if your system has that amount of energy, that means you can just pass that barrier, which makes your system to equilibrate much faster. So that is, I hope I was clear. Was that clear? Do I need to repeat that again? If your system, okay, I will repeat for myself. If your system has a set of potential energy, and if you have, this energy is enough to overcome that energy barrier, which is in a soft system, soft potential energy system, it's much favorable, then you end up with your ultimate energy level. So that is actually shown with these guys quite nicely, that soft potential can be useful to explain the coarse-grained structure of long chains. You can also use it for short chains, but for the longer time of equilibration of polymers, that might be not unphysical. Okay, so that is that. We can now go to DPD. We can at least start to talk about DPD, because DPD is a feature that is using the soft potential. I will also come to that later. Okay, so I will take a sip of water and then start to talk about DPD.
Excuse me, can you switch one slide back?
Yeah.
Well, you said that something about the activation energy.
No, not activation energy. Maybe I misspelled it. So if your system has a potential energy that is enough to, okay, maybe I should draw this, because here in this slide it's not very clear. So you have the potential energy R, and then you have a typical Leonard-Jones, right?
Yes.
So so when you make your system softer, so that repulsion that is going to infinity for a short range interacting particles, that is also becoming softer. So that is becoming eventually finite. So the infinite potential at the short range is switched with the finite potential. So that is what I was trying to say. So if you have, for example, this level of energy in your system, that means 2 beats can pass from each other, which actually making your simulation times or relaxation process much faster. That was I was trying to say. It's not activation energy. So maybe if I said that, I misspelled.
Maybe I just misunderstood.
Okay. So that was what I was trying to say. So DPD is actually introduced by Hugerbrook and Kuhlmann. So actually, because you can also see here the academic life and industry relation, because these guys were at that time working in shell research. And DPD, most of DPD is built in companies, not in universities. So that is also nice. So these are physicists, and in the 90s, shell research was really powerful. It's a Dutch company, Anglo-Dutch company, but they have a huge research facility in the Netherlands. And for the Olatum molecular dynamics and also DPD type of approaches, Shell invested a lot of effort, and they have really nice fundamental papers. So that is also very nice to see what kind of industrial driving force is there for the academic approach. So Hugerbrook and Kuhlmann published this paper in 92, simulating microscopic hydrodynamic phenomena with DPD, dissipative particle dynamics. So they also initially were working on to replacing some lattice-based coarse-grained methods by another method that is aimed to preserve the hydrodynamics. For example, if you insert a particle to a solution, you need to make sure that the rest of the particles are acting by preserving the hydrodynamics in a conservative and properly, and the proper physics should be there. So they were at that time using the lattice-based models, and then they switched with DPD to particle-based methods, and they wanted to aim to calculate the hydrodynamic phenomena, and with of course, the computational efficiency. I will show you later the equations. The DPD is a really simple method, and so they also presented DPD as a simple model that contains dissipation that conserves the momentum. So the momentum conservation is really important if you are considering the complex fluids. So initially, DPD is built for modeling complex fluids, which is also narrowed down to polymers nowadays. Later, Espanyol and Warren, still Warren is working in another company. Pepe Espanyol is at that time in the university, but Paul Warren is working with in endeavor. And they actually came up with a reformalization of the total force term by differentiating or discretizing the total force into 3 parts in DPD. So one of the conservative potential, and the rest is the dissipative and the random force. So here, the dissipative particle dynamics is coming actually from this dissipative force, which was not, which was there for in the original paper of Hugerbrook and Kuhlmann, but Pepe Espanyol is actually worked on to discretize the system to 3 types of forces, and still we are using this notation. Conservative force is responsible from the ultimate structure with all the potential energies there, and the rest of the dissipative and random forces are actually, the Espanyol and Warren came up with this idea that they are coupled, which means if you are coupling with this Gaussian stochastic white noise term, then you conserve the momentum. So that was the idea. So if you want to conserve the momentum, you need to couple these equations, which is actually operating as heat source and heat sink. So one of them is creating some randomness in your system. Otherwise, it will just, the motion of the particles will decay, because you have the heat dissipation in your system. So you need to insert that dissipated heat to your system back in order to preserve the prolonged dynamics. So Pepe Espanyol and Warren came up with this notation. So they said, okay, we can couple this also dissipation and the random forces by the sigma and gamma. So that is also explicitly related to the friction in between the particles. So you need to, when these particles hit, the energy needs to be dissipated, and you need some level of friction in between. So that is also referred as the friction force nowadays. So DPD is mostly this one. So as I already told you, we are when building the effective potential, we are really considering this conservative potential. So later, in summary, okay, I already told that, so I can skip. So you can, for the equations of motion, you can use the Verlet algorithm. But what makes DPD as applicable to chemically relevant systems is came up with this again with the same world, but this time the collaborator changed and it's a RUP root. Sorry, Robert root. There's another RUP root. There's also performance simulation, so you don't need to mix two. So this is Robert root. They're also from the company, and they actually came up with this bit more general treatment of DPD, and they built the procedure to make it applicable to chemically relevant systems. So how will they do that? I will come in a minute. Actually, the title is also nice. So they also bridge the gap between the atomistic and mesoscopic simulation. So which means you have the atomistic data. So previously it was not there. It was more like a toy model, but the physics was there, and they use the physics. They also implement the chemistry, which means you can represent your coarse graining based on your atomistic data. So that is more or less there. So how did they do that? They initially came up with a very simple equation, very soft potential, which I was drew here, which is a finite potential, which goes to maximum level of repulsion of Aij. So the Aij is somewhere here, and it decays. So this is in reduced units. If you are in a reduced unit of 1, your interaction decays. I mean, then you have a zero interaction if you have this level of separation between. But how you choose this Aij? So this is the tricky part. I mean, this is the point that Ruth and Warren worked on, and how they established the mapping from chemical-based structure to DPD level of representation. So they initially built the DPD equation of state because you need that. You need to have an equation of state in order to see and predict how your system behaves. So you need to have a phase diagram, you need to have a pressure component. That's why from there you can switch to free energies, etc., etc. So in order to do that, they built the DPD equation of state. So they also tried different relations. They also tried with the without the excess pressure, without the normalization, etc., etc. So you can, I mean, just read this paper. This is also a very nice paper. I also read, although I'm involved in this field since when? Since 2007. Time to time, I'm still reading this paper. So that's always good to remember some fundamentals, even if you are really expert. So they tried many things, and then they found this relation with the excess pressure and the relation with the density. So they came up with this for a sufficiently large densities, like number densities. They came up with this equation of state. So that is nice. Why? Because then you can start to estimate the thermodynamics of your system because you have the free energy. And here you can see that this non-bonded DPD interaction, I mean the maximum repulsion of the interaction strength. And this alpha is actually, you can see that this settled down. Okay, that is an approximation, of course. I mean, you can also say that I can also take the alpha here, but for the sake of, so coarse grain is always a level of making things simpler. So if you're in a reasonable level of simplicity, you're fine. But you can always go more detailed treatment. I mean, you can, if you are really taking number density 3 or 4 or 2, you can try to estimate what alpha is here. Okay, but what is A? This maximum repulsion strength. So they actually, what they did, so that was really nice, to map onto the Fedorov-Hagen's theory of polymers. Because from Fedorov-Hagen's theory of polymers, you know that the beads or the lattice point or the system that is actually represented by single, or the polymer is represented by equal-sized monomers. So that is more or less the similar idea what DPD has. So they already have the mathematical formulation for the, sorry, this was the continuous version of lattice model, but at least you can represent your oligomer from similar monomers. So that is why they are interested in Fedorov-Hagen's representation. And they have molecules are they want to stay close or they want to stay far. So that is characterized, the chi parameter characterizes, quantifies this behavior. So since you have this energetic term and the chi parameter, if you know the chi parameter, then you can estimate the repulsion. So that is really nice because now you have what you have, you can make your coarse grained beads and then you can estimate from experiments the chi parameter and then you can compute your DPD interaction, non-bonded interaction strength. You asked in the previous session the non-bonded and non-bonded, so this is only for the non-bonded. For bonded interactions, you still use the spring potential. So that is the same, and for the angle that is there. But this is for the non-bonded interactions. So for the chi, actually, so we have so this A and B represents different functional groups. So what you have for the A and A, I mean similar type of piece, because I already told you that fluoroagonist notation gives us similar size monomers or similar level of coarse graining, let's put it in that way. And you need to have the AA, self-repulsion or like-like repulsion. You can change notation by using that. So they actually estimated this AA from the actually experimental data of water. So they have this isothermal compressibility data, and then they have the dimensional compressibility from the experiments for water. And then you can, when you take this one, I mean, from the equation of state, you have this isothermal compressibility, and you have the alpha rho and alpha from here. And then you know that if it's approximately 16 for a number density of 3, you get the like-like interactions, which means the same type of beads are interacting with 25 kT. So that if you are using water, that is there. If your bead, one bead is representing one water molecule, this is how they work. For the AB, for the different pairwise interactions, for the pairwise interaction for different type of beads, again, now you have this one, so you know this, this one was already there, you know also alpha, you know chi, so how can you compute? So that's only one unsolved, unknown parameter. Groot and Warren also worked. They also established for this part, so you know this is a linear relationship from the mapping, and from the simulations they also estimated this line, like linear behavior. If you have a different number density, they have the delta A, the excess repulsion, and the chi parameter relation by a linear line. So that is also a nice feature, because now if you know chi, then you can estimate the delta A. So how do you know chi? So this is what I already mentioned previously. So this is the linear relationship for the different number densities. So for the chi, you have different type of treatments. I mean, one of the mostly for apolar compounds, you have the solubility parameter, which you can either compute from experiments, from a top-down approach by the group contribution procedure of Hansen, Hildebrandt, etc. Or you can also perform some molecular simulations to estimate the chi parameter. So the chi parameter, if the chi parameter is positive, and if it is above a critical value, that means your system will be phase separated, which you will also do some in the hands-on. But if your chi parameter is negative or close to or below this critical value, then you end up with a mixed system. So that's practically, qualitatively, what's going on like this. For apolar compounds, you can have this notation. For polar ones, there is also a modified version of chi parameters, but you can find this in papers in physical chemistry books, so that is there. So that is not an untricky, so it's quite trivial. So in DPD in general, to summarize DPD, so you have a purely repulsive potential, as I already showed you. You have a purely repulsive potential, and the attraction is governed by the relative less repulsion. So in DPD, you have to pay attention. You cannot say this is attracted to this one, but this is less repulsive than this one. Less repulsion means that if you have, so you know, I already showed you that the like or the repulsions are 25 kT, but if they are separated by 30, and if AC is 50, and if BC is 75, of course A and B would like to stay together. So that's more or less what how DPD works. That is very simple. but it's working quite nice for local polymers, other polymeric systems, because you have a top-down approach to parameterize your system, to parameterize your effective potentials. The original DPD, the classic DPD, is actually, as I told you, from Fuller-Huygens mapping, is actually implying the same type of beads, which is valid if a system is phase separated. You have the same local densities. So this is the classical DPD. The bead sizes are similar. That means the volumes around beads or the densities are the same. Of course, this is not quite realistic. So this is now I start where I personally contribute to DPD, because so far the classic DPD is everywhere. But if you really would like to use DPD for chemically specific systems, you cannot always assume that all the beads are similar size. For example, here you see an epoxy, and it's an amine system, is a cross-link system. And if you coarse grain your system, for example, you have these beads which are composed of 6 atoms. So you cannot really coarse grain your system by avoiding and by assuming similar bead sizes. And eventually you might need to encounter some systems which are completely different coarse grain. So this was the system that I was working my PhD, and then we coarse grained the system in such a way that the beads are quite different. For example, the molecular, the bees, that is the cyclic ones are like 150 angstrom cube. But if you go to these ones, the small beads, they are like 2 heavy atoms. They are like 50 angstrom cube. So that is like a factor 3 difference. So that's a problem. So how we solve this one? So if you have this average this factor difference, you need to model a system that is capable of generating some local volume difference around particular beads, because that's why you can make sure that your structure, your end structure, is correct. Because if you have similar, if you have small bead, of course the volume around that bead should be small, and vice versa. Okay, so how we did that? We actually started from the DPD equation of state. So by assuming a mechanical equilibrium between different particles, we have the AIIs, and then with the AIIs you can generate from the same equation of state for the components, and from the excess pressure you can come up with the relation that this excess pressure is mainly governed by this term, and this term gives already us the composition of, if you have, for example, different self-repulsions with A or I bead types and J bead types. So this is the mixing condition. So you have the mixing condition of the geometrical average such that your system is mixed if you satisfy this one. So we already published this in 2013, a long time ago. And we actually started later for the computing the IJ interactions in between as a numerical treatment. We still kept ourselves, maybe I can skip these ones and just come to here. So if you're interested, just go to this paper. If you have questions, you can email me. So we have a numerical treatment, because if your system is symmetric or you have similar sizes, your system already deviates some. I mean, in Groot van Worden is already deviating some from linearity. But for the sake of computational efficiency or parameterization, you get an assumption for the linear part. And then if you do that some prefactor in front of the chi, then you have all the data from different B sizes that is normalized to the same line. That means if you use this type of an equation, you can compute, if you know the chi, you can compute the AIJ. So you have a pressure term that is different than the Groot van Worden, because there it was not there. But here we assume that the system, when phase separated, they actually form mechanical equilibrium. That's why we use the equation of state and assume that the pressure is the same. So if you take a normal, just an average pressure that gives suitable for water, for example, a simple liquid, that's fine. I mean, for different pressures, your system generates the same data. I mean, it's in the paper. For different pressures, we get the same atoms or molecular structure. Okay, I can skip these ones because time is also running out. Yeah, the slide will be there, so you can also go later. If you don't understand, you can email me. But the rest, I mean, when we look to the real system, to the real epoxy system, if the beads are, of course, separated from each other, so we employed at that time the Voronoi tessellation and then observed the local densities around beads, and then we see that from the experiment. I didn't put the experiment. Sorry, because there is also another line, I think, or in another table that we compare this data with the experimental data, but they do. I mean, this approach does reasonably well. You can make sure that the experimental qualitatively and quantitatively we can verify that the volumes around beads are there. I'm sorry, I didn't pay attention to this. Okay. Okay, so this work, I mean, why do you need that? I mean, you need these alternative bead sizes for modeling, of course, different systems, like realistic systems. Plus, you can also try to use DPD with interacting with the hard surface. I mean, hard surface, you can maybe think that, okay, this is a soft potential, how can we make a hard surface? That's a very good question. But if you really increase, so, okay. No. So if you, for example, think a system, a DPD system that's composed of a really high density of layer that is representing solid phase particles, if you make your system high density, much higher than the liquid density, then your system with the increased level of DPD interactions behave like a solid system. That is actually very similar to a, how do you say, you can imagine that you have a volume and then you put a certain number of particles inside and then you increase the interactions in between these particles. What you will achieve at the end, all particles will try to push each other and then they will behave like a solid. So this is the same idea. So you just increase the density, which leads to increased DPD repulsions, and then you can model the solid surface like this. So that is already incorporating a different level of different densities above this solid surface. Because at that time, we were working on epoxy and interacting with alumina. Alumina is a dense layer of fixed particles, DPD particles, with a very high repulsion. And above that, we have different functional groups with A, B, C, D, F are these ones. It's not quite clear, but I mean, all beads are represented by different names. And for each different functional group, we have just a monomer above that surface, and we parameterize these interactions between the monomer and the surface by implementing molecular dynamic simulations with the pure liquid density. That means, in other words, you take monomer A, you make an allotomic representation of monomer A with the same alumina, and then you get a density profile, and then when you normalize this density profile, you get the surface excess, and for different type of beads, at the end, no matter what you take chemically, you end up with a master curve. So we, I mean, this work, we achieved to that one. That means if you know what is your surface excess from molecular simulations, you can read what is your DPD interaction in between that particular monomer and the surface. So I'm emphasizing the monomer because now, I mean that is why we are not considering the whole chain, but instead we are computing the DPD interaction of the monomer with respect to the alumina surface. So that is there. So this is actually, we need to harvest this procedure more because we published this paper and one another paper, but later I stopped working with the surfaces. But actually this procedure is quite nice. I mean, we are getting a lot of citations to that. So if you really would like to use the DPD, so you can start with this one because still, I mean, in the literature, there are not so many people with DPD and parameterization with the solid surface. But that is actually, we compared this data with other coarse-grained simulation methods and atomistic data and experimental data. That is what you see. So you can also see that.
Excuse me. About this research, you said that increasing the interaction, is it something like going from a suspension to a slurry?
You can do that. Because DPD, as I already told you, that it's a more complex fluid representation. So you can play with hypothetically. So we are, in my work, we are always considering the real chemistry inside. But You can also use DPD by assigning arbitrary repulsions and then try to estimate what kind of fluid behavior you have. So that's also really a huge portion of people are doing that, especially physicists. Are you a physicist?
No, I'm not.
But you have a physicist mind, so physicists are always considering these type of approaches, like how they behave as a fluid, and then what happens if we increase the repulsion, and what kind of rheological behavior we have, and these type of things. So that is quite implementable to DPD.
Okay. And another question, why you chose alumina?
Yeah, at that time we were collaborating with a company. It was a semiconductor company. They have this all kind of alumina metals that is covered by epoxies.
Mm-hmm.
It was a microelectronics approach plus an aerospace approach. So it was a different consortium. So we had microelectronics collaborators, also aerospace collaborators. So they are using as a coating material.
Mm-hmm.
That's why.
Thanks.
But at the end, it was quite. We end up with a quite scientific side. I mean, we started from an industrial problem, but then we developed a lot. So this was more or less what I did my PhD. So in my postdoc, we start to work on the hydrogen bond. Why hydrogen bond? Hydrogen bond is attractive. So I told you that the DPD is repulsive. So that's quite important if you really would like to model some liquid mixtures, because if you really would like to get the some chemical data associated with, for example, negative excess. The excess volume. So this is this. So if for classical DPD, if you do bead, alternative bead size, whatever, classical DPD, you always get the positive because you have always repulsion in between. But the experimental data says that should be there. So then we start to work on the hydrogen bonding implementation, because we need to explicitly treat for the system that needs to have the hydrogen bonding system, because we don't have the negative chi parameter. And at that time, we were also doing it with a project which is actually composed of some polymer material, and there was, if there is a damage with the polymer, then some functional groups will migrate to the surface, and they do this in water. So that means you need to treat explicitly the DPD modeling of interactions between the monomers, polymer monomers, and water. So there you need the negative, the properly model the physical properties of that systems, plus the to make it applicable to more general field. Okay, I can skip this one. So how did we do that? It's actually, the idea is again not quite complex, but we treat with the Morse potential. So you have this Morse potential. So this is a usual implementation of the hydrogen bonds. As I told you, the trading force field already uses a Morse potential to treat the hydrogen bonds. So hydrogen bonds is directional, but in DPD you have the time scale. The time steps are much larger than the hydrogen bond formation and dissociation times. So this is just an effective attractive potential. So you can think of as such. Here two parameters required. So we compute the R0 and D0 from the molecular simulations, and we tested the case for methanol water, ethanol water, and 1-propanol water. I can skip that. So we end up with the Morse potential parameters here. And then, okay, I will skip these ones. We came to the results that for methanol water, we really nicely predicted the experimental negative excess. Plus, the alternative bead sizes already give us the asymmetric behavior. So if you go to 1-propanol, because we have a huge size difference, with here, 1-propanol is 1 bead, water is 1 bead. 1 water is 1 bead. So that's why the size is different. We get the asymmetric behavior. So we predicted these nicely. We also started to work on an air and the mixture of alcohols, because alcohol-water mixtures are known to exhibit surface enrichment near air. And then from experiments, we say that the DPD simulations at higher concentration regime are much in line with the experiments. So here, it's a problem with the modeling of air and also the statistics, because in DPD, of course, you have much statistical error because you have a fixed number of particles. But if you go to higher alcohols, which means you increase the number of alcohol particles in your system, we end up with a nice agreement. So we later moved to the more complex systems with this hydrogen bonding issue and the alternative bead size issue with the polyethylene glycol, oligomers and water interactions. The negative excess volume is nice, so this is classical DPD. So sorry, without the hydrogen bond, this is with the hydrogen bond. And without the hydrogen bond, you see that this phase separating, which is quite unrealistic, but you need to, of course, have this type of system. So that's quite nice. We also saw, I also worked on later with the single pack chain conformations. So that is important because here you see that this is a physical property of polyethylene glycol, but what happens for the individual chain structure, for the conformations? So how are we there? How are we doing with DPD? Because in DPD we just have the repulsion, Morse potential, bonded interactions, and angle potential. That's it. So we don't have an alloton treatment. And for the polyethylene glycol, so if you, so the experiments say there's a huge degree of helicity. So you can, I wrote a code at that time to characterize the helices. So it's not like helice like DNA or RNA. So that's different than that. But all chain exhibits some degree of helicity. So we sort, and that is experimentally known that that is much increased with the addition of water, which is acting as a lubricant, and we also observed there. So that is, I mean, you see that these are nice portions here. We don't have, but at least we have some degree of helicity here. But in a simple model, I mean, if you can get that, so that is quite, I was quite happy. I mean, the reviewers were also happy. We published this, I published this in PC.
Is this helicity 3D?
Yeah, 3D. And all what I'm talking about is 3D. We don't do 2D. Later, Hakan there is worked on the collaborative project with Thomas from Ljubljana, Slovenia, to increase. I already told you that one alcohol was 1 beat, but there we were missing the hydrophobic-hydrophilic balance. So if you, for example, make a coarse-grained representation that makes the hydrophobic groups as 1 beat and the hydrophilic group as 1 beat, then we will be more versatile, and we can end up with the more generic parameterization for DPD. Some people can take as a hydrocarbon group and use in a different system. So Thomas, our collaborator, actually established a three-dimensional Mercedes-Benz model with an analytical model. So we use this analytical model to compute our interactions. So very briefly, we have a chemical potential, and the chemical potential is composed of some statistical term, which is composed of different level of interactions. And we have the hydrogen bonds, Leonard-Jones, which we used as a DPD type of partition function contribution, and the non-bonded or the ideal gas term. And then we have experimental chemical potential data from literature, and we can compute the hydrogen bond interactions in between only the hydrophilic groups. So that is why did we do that? We wanted to compute the hydrogen bond interactions only for the hydrophilic groups, which is OH, between OH. So again, we studied the similar system. We estimated a lot of properties. Later I will show you how we computed that. But for the RDFs, for pure water, so this is classical DPD, and this is atomistic. So Hakan did all the atomistic simulations there. We also compared with DPD, so we also have nice estimation with methanol, ethanol, and 1-propanol. That's quite, here you can see that you cannot do this with classical DPD, so that's quite nice. So this is actually three-body angular distribution. Might sound a little bit vague to you, but three-body angular distribution is how the three molecules are distributed in space. So you take one bead, you draw a cutoff, and you compute the angles of all the possible all the possible angles that are formed from this neighboring three particles. And you get the distribution. And for water, for methanol, you always have this bimodal distribution, which is indicating there is some sort of local structure, which is also experimental now, but nobody has characterized this before. So a lot of people also spend so much time in atomistic simulations, but even in a DPD, in a very simple model, you can estimate this local structure. So it's really nice. And you can also differentiate with hydrophilic, hydrophobic. Sorry, this should be hydrophilic. I still need to, so this is not correct. Hydrophilic, hydrophilic, hydrophobic, hydrophobic. So you have this. So there is a gap here that already gives us. We also should treat the hydrophobic interactions explicitly. So that's now we are starting to learn this. But nevertheless, we also computed the transport properties from Kubo formalism, and so that is also a very nasty procedure. You need to take care of the pressure, shear viscosity. So here you see it's quite nice, and also the thermodynamic properties like as a thermal compressibility, how the procedure behaves in different temperatures. So if you have different temperatures, you have really nice agreement. So in propanol is a bit slight, they're off at this point, but the rest is quite nice. Even in water, you have this asymmetrical critical point. So that is really nice. So we recently published this in Journal of Molecular Liquids. So this is a master thesis work of Hakan. So now we didn't publish this yet. We still need to write this. We also worked on mixtures, but for the RDFs, for the mixtures, we take different mixtures for DPD liquids and then the same system, but this time with the mixtures. So we have really nice RDFs. Now we're trying to compute the other properties. What are we doing else? So now DPD, now I'm trying to show you because now I think I have to stop at 15. Now that's why I'm going fast. So if there's something unclear, just we can talk after the lecture. What are we doing recently? Deniz is working with the polyurethane coatings. That is a coating system that is known to exhibit some involving dangling chains. So if you change the environment, how this dangling chains moves between the bulk to the surface, how the diffusion is there. So this is also a collaborative project with ERA, with the TÜBİTAK bilateral project, and the people, the collaborator from Iran are doing Martini simulations, Martini type of coarse grain, and we observed that we have a really nice comparison between DPD and Martini type of system. So we studied many things. So if you're interested, Deniz's paper is also just accepted 2 weeks ago, or something like 2 weeks ago, in Progress in Organic Coating. So it is there in Google Scholar and the web page, but it's not there in Web of Science yet. It takes time. But we studied also the diffusion behavior, the local structure, etc., etc. Now we are carrying this work by. Oh, I will tell you. Okay, I will tell you in the hands-on session. We are carrying this work further on to perform atomistic simulations. What else we are doing? We are also working on blockopolymeric systems and drug encapsulation. We can estimate the experimental, we can also quantify how the system is structured, what the structure is, how the system is encapsulating for different concentrations. Here you see a snapshot of the MyCell system. So these are experimental relevant systems. Why ibuprofen? Ibuprofen is a very simple hydrophobic molecule. That's why I took it. That's why. It's just a toy model because at that time I was just into that field, But with DPD, you can see all kind of morphology with different, like you can get the phase diagram, you can have the quantitative information about the direct encapsulation for different systems, for different block polymers. So this is PLA. The hydrophobic group is PLA. Here it was PPO, polypropylene oxide. So these are biodegradable polymeric systems that are candidate molecules to encapsulate drugs. So you can get the drug encapsulation, you can also estimate drug release, you can get the release kinetics and try to fit to a non-drug release kinetics models like PEPMAD model or the Japanese guy, I forgot. So we also published this one. We also worked on the PLGA, for the stimuli responsive, like if you change the temperature, they have a different morphology, very slight shift. We also worked on that, but at this time only we studied the encapsulation behavior. So this work needs to be continued, so a portion of the work is there. And lately we have a project, TÜBİTAK project is about the mRNA carriers with DPD. What we are trying to build is the liposomes, and we will try to incorporate the mRNA and try to mimic actually what's going on with the molecular structure of the traditional or the mRNA vaccines that we are using actually. We started with DPD build some. Actually, this is also the picture that you saw in the EuroCC web page. We started to work also with different molecules actually. We wanted to encapsulate coenzyme Q10, so this is actually a collaborative project that is with our pharmaceutical department. So we also would like to go to mRNA and also hydrophobic drugs, so such that we can encapsulate mRNA and other hydrophobic drugs together if that's possible. Or Now we are trying to estimate the molecule. The example, so this is from literature, this is not our work, but I can skip this, so since you will have the presentation later, you can have a look at this. Because I found these papers quite interesting, because they have polymeric self-assembly, so they have a direct encapsulation, and they compare with XRD in this work, and they also study with different micellization behavior. We also do that, but that's also nice to do with different systems. And for the pH responsive polymer drag loading and release applications, DPD is quite useful. You can also study with DPD gold nanoparticles with Sirna and polymers, like composites, and you can put composites. And also you can correspond to different micellization and compare with your electron microscope results. You can also try to receptor-mediated endocytosis with DPD, that's also possible. Of course, you need to be careful, but if you are careful, if you do everything correct, you can model these type of really complicated systems with DPD. Okay, let's come to the hands-on session. What are we doing in the last 5 minutes? I will tell you about what we're going to do in the hands-on session. In the first one, we will try to see the phase separation of monomers. So we have a mixture of A and B, and it's 1-to-1. We will just try to increase this repulsion between the AAB, which I told you, and then we will start to see how this is gradually phase separating and in which value the chi will change. The second one, the micelle formation. So we have, we will monitor the micelle formation process. We have, I mean, here in this one we will not change the DPD parameters. The DPD parameters will be fixed, but we will see the effect of concentration and three different types of, I mean, AB type dipole copolymers, oligomers in solvent, but the X will change. So we will have different chain lengths. So this will be that, and the final one will be about the cross-linking. I particularly know there is one person in the audience who wants to learn about the cross-links. So we will try to model the chemical reactions in DPD. How do we do that? What kind of constraints we need to assign, and what if these constraints are is changed? I mean, what will happen? How this cross-link conversion curve will change? So we will see in an ADVA oligomer and star-shaped cross-linker. And we will try to plot the dynamics of cross-link formation. What we will compute, the RDF, the radial distribution function, is practically how the particles are distributed, I mean the local structure is characterized. So this is how we compute. So we will also, I'm going fast because I have like 2 minutes now, but I will also tell you in the hands-on session when you're doing stuff. We will also try to estimate the isothermal compressibility from the volumetric fluctuations. Of course, our simulations are short. There is a huge error, but we will try to do our best to get the proper values. We will also plot mean square displacement and the diffusion of the beads. Well, the average diffusion, of course, we can also make it to particle, compute this for particular beads. We will also compute cross-link conversion for the last case. So that is actually uniform beads over N total, and that's the profile. Okay, I think I'm done. It was the second part of the lecture was really fast. I hope I gave you a brief information of molecular dynamics, soft matter, molecular dynamics, coarse grain, and DPD in general. I wanted to show also some complicated molecules that what you could do with DPD, and let's see how it will go for the hands-on session. Okay, I'm finished.